Well, good evening. So we are on the 5th day of our webinar series, and we have two wonderful speakers today. So first we'll have Dr. R.P. Prajapati from the university, from Guru Ghasidas University. And next we'll have Professor Dimitri Batani from the University of Bordeaux, France. So a few words before I start the show to this evening. So a few words about Dr. Prajapati. Dr. Prajapati did his BSc from Madhav Science College, Bikram University in Ujjain in 2002. In 2004, he completed his master's from the same university, Ujjain, and secured the university 5th position. Wonderful, sir. And then he completed his PhD under the supervision of Professor R.K. Shahjalani from Bikram University. And the title of his doctoral thesis is A Study of Hydromagnetic Instabilities of Gaseous Plasmas. So he has got more than 11 years of teaching experience. He joined Guru Ghasidas University, Bilaspur in July 2011. And thereafter, he carried out some postdoctoral research from IPR Bhat, Gandhinagar. I missed. He initially carried out the postdoctoral position in IPR and then joined as an assistant professor in Guru Ghasidas University. So today we have him amidst us. He is a senior to us all. And sir, so today, just a minute. So today his talk would be a bit interesting. It is neutrino plasma interaction in degenerate plasma. So listeners and students, scholars who are online, please put your queries and questions in the YouTube chat box. So we'll convey them to the speaker and he will answer them. So let's give a heartfelt thank to Dr. Prajapati. Sir, please.
Thank you very much, Swarniv, for having this good opportunity. And really, it is a very nice platform to have organized this scholar colloquium, especially to train the young research physics. So I appreciate your and your all team efforts to organize such kind of activity. So, as Swarniv has already told any more about me, so without wasting any time, let me start my today's talk. Today I am basically going to discuss you with the neutrino plasma sections in degenerate quantum plasma.
Sir, could you just move your position because signal issue is there. Your voice is breaking. Just a bit. I think it will go.
Yes. Just give me 1 minute, okay? Let me check
sure,
my signals.
Sure. Thank you.
Yeah, now I can hear you. Now I think you can hear me.
Yes, it is absolutely fine right now. Thank you.
Okay.
Thank you.
I think host has disabled participant sharing is screen sharing. So I am not able to share my screen. So can you help me? Hello?
Yes, it is shareable right now. Please try.
Okay, okay. Now I can see. Thank you. Thank you very much. So let us start the discussion on the neutrino plasma interactions. Yeah, in degenerate quantum plasma. So the outline of today's talk are is there any problem? Okay. So firstly, I will tell you about the fundamentals of degenerate quantum plasma, then motivations behind this work. Then we will discuss about the neutrino beam plasma interactions in dense plasma, how the neutrinos are interacted with the plasma particles in the highly dense plasma. Then whenever we talk about the neutrino beam plasma interactions, and especially in dense system like in Dwarf and neutron stars, so the process of collapse of these systems under the influence of gravitational instability is a very interesting and hot topic. So I will discuss about the gravitational instability, and a brief review is done. Then in order to study the waves and instabilities in the neutrino modified magnetized plasma, we have formulated the neutrino MHD model and some results and discussions of our recent problem. And lastly, I will summarize the problem. So in the before lectures, you have all gone through, I think, the fundamentals of the classical plasma, the dusty plasma, and now let us discuss something about the fundamentals of the quantum plasma. So as you all know about the classical plasma, that it contains the charged particle like free electrons, ions, and exhibits the various property like collective behavior or uh, congenital behavior, and they satisfy plasma particles satisfy the Maxwell-Boltzmann distribution law. Here in the case of quantum plasma, the statistics and the behavior of the particles are quite different. So as we know that any microscopic particle which is moving, it exhibits the wave behavior. So the similar thing is here, that when a moving electron which behaves like a wave also, so if the de Broglie wavelength of that electron is comparable to the dimension of the system, it may be the gyro radius of the system, or it may be the scale length of the system. So in that case, the particles exhibit a very unique behavior. The plasma does not remain a classical one, but it is called the quantum plasma. So this type of environment is possible only when the density of the system is very high and temperature is very low, because the quantum corrections are possible only at the temperature below the Fermi temperature. So in the extremely high density plasma, say in white dwarf having density 10 power 34 per cubic meter, the temperature is very low here. So the gas in the white dwarfs behaves like a ideal quantum gas, and that consists the degenerate electrons. And these degenerate electrons, they follow the Fermi-Dirac distribution. They satisfy the Pauli exclusion principle, and their dimension, their de Broglie wavelength is comparable to the dimension of the system. So now we have such a kind of new environment in which we have the degenerate electrons and ions and holes or other charge carriers or neutral particles may be there. So this kind of plasma having very high density, low temperature with degenerate electrons whose dimension is comparable to the de Broglie wavelength of the system, that is called the quantum plasma, or it is also known as the degenerate quantum plasma. So few things you should know, that the de Broglie wavelength of the charged particle must be comparable to the interparticle distance or that is possible only when the plasma is highly dense. That is, the density must be larger than 10 power 30 or larger than this value. The second criteria is that the temperature must be smaller than the Fermi temperature. So obviously, this type of plasma is very different than the classical plasma, in which the temperature is very high. So classical plasma is basically a low density and high temperature plasma, where all the particles they are followed by the Maxwell-Boltzmann distribution. But in the quantum plasma, the particles obey the Fermi distribution. Now, what is interesting that when we consider this type of system where there are degenerate electrons, so what kind of important quantum effects can take place in the system? So there are majorly, if we say, there are three important factors that we should discuss in this degenerate quantum plasma system. One is the quantum statistical pressure. That is, here the pressure is given by the Fermi pressure, which incorporates the Fermi velocity of the charged particles also. And here the classical potential, it does not remain the classical one, but it is defined by new potential that is called a Bohm potential. So the detail of this Bohm potential is already given by David Bohm in his very famous paper, which is published in Physical Review. So this incorporates basically a potential term and whose negative gradient gives us the force. So that force can be taken into the dynamics of the degenerate electrons. If we talk about the spins of the particles, so these electrons or positrons, they have angular momentum spin. So due to the spin produced in the plasma, there are several interesting effects like electron spin magnetization. It largely affects the various phenomena in this degenerate system. And the average energy is here given by 3/5 of the Fermi energy. So if we see that where we can expect this type of quantum plasma, so with the help of this picture, I can show you that which is basically a relationship between temperature and electron density. So you can see the various regions here in which we see that in low density and high temperature region we have the magnetic fusion in which the plasma is classical, and we cannot expect the quantum corrections here. If we go towards the higher density region, so we have the dense stars like planets, like interior of the neutron star or white dwarf star. And even in the inertial confinement fusion, the plasma exists in very high density. So the density is almost comparable to the density of the white dwarf star. So the quantum corrections are also important in the inertial confinement fusion device. So these are the systems where we can consider the plasma is a cold degenerate quantum plasma. And these plasma particles have the interparticle distance of the order of 1 by n power 1 by 3, and the quantum effects appear in the system when the de Broglie wavelength is comparable to the interparticle distance. And the criteria of a plasma to be called the quantum plasma, that the product of the plasma number density and the cube of the de Broglie wavelength, it must be very large than 1. And obviously there is no any change in the plasma frequency, so it remains as usual. There are various workers who have considered the quantum plasma in various kinds of plasma environment, and these are some references where you can see that Manfredi and Haas, they have studied the quantum effects, collective phenomena in the plasma in the quantum electron gates. Then in quantum Coulomb crystal, Bonnier have reviewed this, has reviewed about the formation of the quantum Coulomb crystals. And even in laboratory devices, say in metallic nanostructures or in ultra small electronic devices or in plasmonic devices, there are so many quantum corrections like tunneling effect or Bohm criteria, which takes place, and these quantum collections, they modify the various phenomena in the particular type of plasma. So these are the domains of the quantum plasma. So obviously the density must be very high. If we say particularly in the astrophysical environment, say white dwarf star. So white dwarf star is the best example of the dense degenerate quantum plasma. And at the end of white dwarf is basically formed to the end stage of the stellar evolution. And this dwarf star contain the degenerate electrons, where electrons they are followed by the Fermi-Dirac distribution. And the white dwarf, it is recently reported by some authors that these dwarf stars they also carry some dust grains of graphite having mass 10 × 10 or 80. But there are several questions on the existence of dust particle in quantum plasma, and it is really a topic of question now, that whether the dwarf stars or neutron star they can carry dust particles or not. So white dwarf star is basically a dense star having mass 1.4 solar mass. Its mass should not exceed this limit, Chandrasekhar mass limit. Its size is very smaller than the size of the Earth, but it is almost comparable to the size of the Earth, but the size is smaller than the Sun. And it is a highly magnetized system. So the magnetic field is around 100 to 200 Tesla. And there are two important pressures here. One is the gas pressure, Fermi gas pressure due to the degeneracy of the electrons. And another is the pulling due to the gravitational force. So basically in the dwarf star, we can say that there is no any role of the gravitational force, because here the collapse is mainly due to the degenerate electrons, that is due to the Fermi pressure. There is another example, that is neutron star. So in neutron star is basically a collapsed core of massive supergiant star, which has a larger mass as compared to the white dwarf, and its mass is 10 to 25 solar masses. And neutron star is having different entity, like it contains here the neutrons, and as in case of white dwarfs, the electrons have degeneracy pressure. So similarly, in the neutron star, the neutron degeneracy pressure takes place, and neutron stars they are supported by the neutron degeneracy pressure instead of the electron degeneracy. So this is the major region in these two systems, where the one consider the electron degeneracy and neutron star consider the neutron degeneracy pressure. This is the important parameter, Fermi temperature. So as we have already told that the temperature of the system must be less than the Fermi temperature. So we can calculate using this very simple expression. If we know the number density of the system, so you can calculate the Fermi temperature. And if this temperature is, if the given temperature of the system is less than this temperature, so you can expect the system to be called as quantum plasma. Another measure to check that whether the plasma is degenerate or not, there is a coupling parameter chi here. So this quantum coupling parameter, which is the ratio of the Fermi temperature and the temperature of the system. So if this temperature is very high, that is the Fermi temperature is very large than the plasma temperature. So you are talking about basically quantum region. But if the Fermi temperature is very small than the plasma temperature, gas temperature, then you are talking about the classical region. So these are the two parameters by which you can check that a given system is whether a classical one or quantum. So now how the neutrinos takes place in the interaction with the plasma. It is a very important topic. Basics of neutrino. The neutrino is a kind of lepton elementary particle, and there are three types of neutrino. So these are basically produced due to the weak interaction in the plasma. Reaction, sorry. And these three types of neutrino out of which electron, neutrino, muon, and tau1. The electron neutrino is having, obviously its charge is 0, but its spin is half. It is also discovered that the neutrino, they have the mass also in terms of energy unit. So basically the neutrino was predicted first by Wolf-Pauli in 1930, and he won the Nobel Prize in 1945 also. But experimentally, this neutrino was discovered by Clyde Cowan and Fred Dennis in 1959. So earlier it was assumed that the neutrino are the massless particle, but later in 2015, Takaki Kajita, Japanese professor and US professor Abby McDonald, they experimentally investigated that neutrino, they have the mass. So basically they have found the neutrino level oscillation in their famous detector, that is super Kamiokande detector, which was established in the Japan. So they found that the neutrino, they have some finite mass also. So this gives basically an idea to us that if neutrinos, they have some mass and they are interacted through the weak interactions, and our plasma especially, which consists electrons charged particles that are interacted through the Coulomb potential. So basically the field of neutrino plasma interaction is basically the interaction between the weak interaction and the electromagnetic interaction. So this type of interaction can take place in the various astrophysical environments, like in supernova explosion. So in supernova explosion, there is a neutrino sphere in which a huge amount of neutrinos, they are emitted. And these neutrinos, when they interact with the plasma environment, so we can expect the several types of neutrino plasma interactions, and we can expect the propagation of several types of waves and instabilities. So this was just idea I got when I met with Professor Takaki Kajita in Australia during the APPC conference in 2016. So I discussed with him that is it possible to integrate the neutrino with the plasma particles, and let us first we see their roles in the case of gravitational instability or fundamental waves. So his answer was very positive, and he told that you should discuss these effects in the case of gravitational collapse, and especially in supernova core collapse, they may be very important. So I just started to work, and I worked on the problem of influence of neutrino beam on the gene's instability in magnetized quantum plasma, and that was published in 2017. So our aim was to discuss the influence of neutrino beam on the dense systems like Dwarf star, and especially we have focused on the gene's instability. But more than this, the investigations of fundamental waves like ion acoustic wave or linear and non-linear waves, they are investigated by a large number of researchers nowadays, and they have just modified all the classical waves in the including the neutrino contribution. They have proposed several new kind of neutrino modified waves. So these types of waves, they can be expected in the core collapse supernova, in the interior of 5 dwarfs, in crust of neutron stars, in supernova explosions also. So since the neutrinos are weakly interacting particles with matter, and they in this way they play a crucial role in order to transfer the energy from neutrino through the neutrino beam to the plasma particles. And when they transfer the energy to the plasma particles, so due to the excess energy gained by the plasma, several types of wave can be excited, and these waves and instabilities, they are of large interest, and we should discuss on them. So how this physical mechanism takes place there. So if we see here in the neutrino sphere of this core collapse supernova, we have when there is a explosion, so during the supernova explosion, it is in the range of 100 to 200 kilometer from the center of explosion, and around which a very luminous neutrino beams are propagated everywhere. So their energy is very high, 10 power 53 R per second, and their intensity is very high, 10 power 30 watt per square centimeter. So this type of environment basically form a neutrinosphere.
So just to interfere 1 second.
Yes, yes.
At the network, your voice is breaking. Just regarding the bandwidth, can you just turn off the video for? Can I turn off if it helps?
Yeah, you can do, no problem.
Okay, sure. Just checking. Carry on, sir.
Now
it is clear.
Okay, thank you. So during the supernova explosion, when these neutrinos, they are emitted and they interact with the plasma. So there is an interaction between the neutrino and plasma. So the excess energy, very highly energetic neutrinos, they push up this plasma and they exert a pressure, due to which a very high energetic shock waves are created here, and they takes place in the various plasma interactions here. So these are also expected in the structure formation when we study the collapse formation of the dense stars. So let us we just discuss the influence of this neutrino in the case of collapse of a self-rotating matter. So the collapse of a self-rotating matter basically deals with the fundamental Jeans instability, and the Jeans instability is basically the instability which is produced due to the combination of two pressures. One is due to the thermal pressure exerted by the plasma particle, and second one is the gravitational force due to the own gravity of the system. So from the molecular cloud, when this collapse happens, and when excess gravity, inert gravity, it exceeds then the thermal pressure. So there is a collapse occur, and when it satisfies the criteria, mass is greater than the Jeans mass. So there is a fragmentation of the cloud, and in this way, the star formation process takes place here. So here in this case, the thermal pressure cannot support the gas cloud against the same gravity, and hence the cloud collapses and it fragment, and the formation of stars take place. So this type of this Jeans instability is very common in the large and small scale structures, especially in star formation, in interstellar media, in nebula, in molecular cloud, and in dense star also. So recently, there are some studies where the effect of neutrino beams have been considered to study the waves and instabilities. So Bingham et al. Have studied the long wave, which are the very fundamental electrostatic wave. So in taking the contribution of neutrino, they have investigated the long waves, and the electron plasma instability produced by nearly monoenergetic neutrino beam with flavor oscillation is investigated by Mendoza. Haas group, they have taken several effects like neutrino oscillations, or the electron ion coupling, or the ion acoustic wave, or other kind of non-linear waves they have investigated. So there are various studies in which we can see that the neutrino and plasma interactions, how they modify the fundamental waves and instabilities. So these are some very interesting references. You should go through them, and you can see that very basic mathematics is there, and how the basic fundamental waves are modified, including the neutrinos. So now our question is that how the energetic neutrino beam plasma interaction take place in gravitating degenerate non-relativistic plasma especially, and what is the role of these neutrinos in the gravitational collapse of supernova and white dwarfs. So we just formulate a theoretical model answer these questions, and let us we discuss the effects of the neutrinos on the core collapse process of supernova and white dwarf. So I will take the simple equations that for the neutrino part, the influence of propagation dynamics of intense neutrino beam, we will consider here the neutrino momentum transfer equation. So this is a very fundamental neutrino momentum transfer equation, where we have considered here especially the plasma is non-relativistic, and the motion of these electrons basically here generates the electric and magnetic field. So these are the electric and magnetic field effectively produced in the system, and we have a neutrino continuity equation. So this is a neutrino momentum transfer equation. We will couple it with the equation of motion of plasma particles. So I am here considering the single fluid equation, not taking the different electron ion entities. So I am taking here a single fluid MHD equation. So the and that model is very standard, which is derived by Haas et al. That we consider the separate equations for electron ion and then couple together, and we get the reduced equation. So for plasma, we have two equations here: the continuity equation, and the second one is equation of motion. So when we couple these equation of motion of plasma with the neutrino, so we have additional term here F nu by mi, and F nu is here, it is the effective force produced due to the highly energetic moving neutrinos. So see here, it is clear that the moving neutrinos, due to their density, they are producing here the electric field and magnetic field, and these are coupled with through this force in the equation of motion of plasma. In the remaining equation, like magnetic induction and Poisson equation, they are also considered here. During the solution, we get a term in the magnetic induction also due to the neutrino force contribution. So now we have a simple set of neutrino plasma equations. And these equations, they are linearized using the standard linearization method, and we consider that perturbation of the type of exponential, and we just do a very simple exercise which is given in a famous book, Bittencourt also. So we get the dispersion relation of the system. This is the dispersion relation which we obtained here. So if I neglect here these two terms, that is this one, which is due to the quantum correction, which is also called the quantum diffraction term or the bomb potential term, and this second one is the term produced due to the neutrino contribution. So these two are the additional terms which are obtained here. So for simplicity, let us discuss this dispersion relation in two cases. First, in the transverse case. So in the transverse case, where we discuss the propagation perpendicular to the magnetic field, and especially for perpendicular propagation. So you will see that here this term vanishes here when k is perpendicular to u1. So this whole term vanishes here, and there is no any quantum corrections or neutrino effects are observed. And in the transverse case, when we discuss about the parallel propagation, so we get the here quantum magnetosonic wave modified due to the neutrino. So see here, we know these two fundamental propagation in plasma, parallel and perpendicular. So here we can expect that the neutrino, when the neutrino beam propagated parallel to the propagation of the plasma, then we can consider then we can expect only the neutrino effects in the wave propagation of the plasma. So a parallel beam must be propagated in the plasma so that it will be effectively modify the fundamental MHD waves in the plasma. Let us discuss a oblique case propagation. So in the oblique case propagation, we have simplified our dispersion relation, and we get here this dispersion relation finally, which incorporates here two terms. One is the Vn, and Vn is basically here the neutrino speed, it has the dimension of speed, so it is called the neutrino speed. And second is the quantum bomb potential or quantum diffraction term here. So these neutrino beam effects, they also vanish if we consider here the uh, perpendicular propagation. From this case, we can here clearly see that if theta is 90 degree, that is especially when we talk about the perpendicular propagation, so this term vanishes here, and we have simply this term Vn square c square. So this additional term due to the neutrino beam velocity, it exists only in the case of either parallel propagation or in the oblique propagation. So there is no any question of discussing this dispersion relation in the case of perpendicular propagation. So we can discuss this in the oblique or in the parallel propagation case. So let us now we calculate that what is the growth rate of this neutrino beam modified instability. So the growth rate can be easily calculated, that if we have here two parts, one is the imaginary and real part, and this imaginary part here gives us the growth rate. So the simple expression of growth rate can be derived here, and this gives us the instability criteria. So obviously when this term is larger than this one, so this will be positive, and there will be growing instability will be observed here. And for parallel propagation here, theta is 0 degree, so cos 0 is 1. And if we consider the ultra relativistic neutrinos, that is their velocity is comparable to speed of light. So we see that here no neutrino beam effect will observed, and only quantum magnetosonic mod will be observed here. Because when we will put here theta is 0 and u nu is equals to c, so every simplified dispersion relation will be obtained here, because here this term will be vanish here, and there will be no any growth rate will be observed. So only we will get the remaining magnetosonic mods only. And the growing instability will observe if this gamma prime is larger than 0, and especially it is the growing instability will be larger for perpendicular propagation when u nu 0 is perpendicular to k. So when u nu 0 is perpendicular to k, that is when theta is here 90 degree. So when we put here cos 90, that is this term will vanish here. So we will get Vn root k upon this term. So the growth rate will be maximum here. So we can say that here neutrino beam instability growth rate is larger for perpendicular propagation. But what about the insensibility? So when we consider the oblique propagation, taking theta equals to pi by 4. So in this case, we have a simple dispersion relation of the genes term modified dispersion relation. So this magnetosonic mod is basically modified due to the quantum wave speed and the neutrino speed, and this is a genes term here. So we can easily get a genes criteria of instability. So if this term is less than 0, so obviously there will be a negative imaginary root, and there will be imaginary root, and this imaginary root will provide us instability. So this will be possible only when k is less than kj. That is, if the perturbation wavelength is smaller than this order, so our wavelength lambda is larger than this value, so then there will be a genes instability will be observed in this system. So we can reduce the system, we can reduce the results in classical, we can compare with the previous published work also. That is, if we ignore these three speeds, that is sound speed, Alfvén speed, and this quantum wave speed. So we have a very fundamental genes wave number expression modified by neutrino beam. So from this expression, by putting the neutrino energy beam, neutrino density, you can calculate that what should be the genes wave number below which there will be genes instability observed. And from this expression, we can say that the critical genes wave number is directly proportional to root epsilon nu 0, that is root of energy of neutrino beam, and it is inversely proportional to root of n nu 0. So obviously, when the neutrino beam energy will increase, so the critical genes wave number will increase, and if the density of the neutrino beam will increase here, so Kj will decrease. So we have calculated this critical genes wave number for the core collapse supernova, taking the neutrino beam energy 10 MeV. So we have the critical wave number, genes wave number, nearly 10 power 8 meter. So we have chosen this parameter and applied our results to understand the neutrino plasma interaction in core collapse supernova. And for this parameter, we get the genes time scale, which is nearly 1.25 second. It is very interesting to know that this time scale is almost comparable to the explosion of the supernova. So the supernova explosion time scale is 1 second. So we can say that both the genes time scale and the supernova explosion time scale, they are comparable. So we can expect, or we can consider the neutrino effects in the case of genes instability also. And the time scale of neutrino beam instability is observed, which is very smaller than the genes time scale. So this time is obtained 0.51 microsecond. So it means that here the this neutrino beam time scale is very shorter than the genes time scale. That is, the neutrino driven instability is fast enough to alter the mixing in the gravitational collapse of supernova. Since this time scale is very small, so neutrino, they very fastly enter into the gravitating plasma, and they affect the collapse of this supernova, and finally when the burst occurs, so due to the excess energy gained by the neutrinos, the explosion occurs here. So before that, there are several interesting interactions which we have discussed. They takes place there, and the fundamental waves, they are modified, and the neutrino beam instability and the genes instability both are modified. If we see numerically that what is the how the neutrino beam energy affects the growth rate of genes instability, so we have simply plotted the growth rate of genes instability versus the wave number. So we see here that when we increase the neutrino beam energy, so there is decrease in the growth rate. So due to increase in the free energy of the neutrino beam, the critical genes wave number and unstable region both are increased here. So we can say here that the neutrino beam energy basically destabilize the growth rate of the genes instability. And there is a critical wave number. It is around 10 or 8. Larger than this, there is the unstable genes mods are observed here, and below that there is a stable mods are observed. The reason is very simple, that is because the genes criteria, it provides the necessary condition for the collapse of supernova, and it involves with the release of gravitational energy. So the excess energy, neutrino energy, it causes to destabilize the system. So obviously, due to the excess energy of the neutrino beam, there is an enhancement in the growth of the genes instability. On the other hand, if we increase the density of the neutrino beam, so for a lighter neutrino beam, the genes instability growth rate is here larger, but as the neutrino beam density is increased, so the unstable region, it decreases, that is, it stabilizes the growth rate. Means we can say that when a dense neutrino beam will enter in the plasma environment, and its density, if it is increasing continuously, so there will be stabilization in the genes mod which are produced due to the self gravitation force there. So from these two points, we can see here that neutrino beam energy, it destabilizes the growth rate of genes instability, while the neutrino beam density, it stabilizes the growth rate of genes instability. So these are only just two parameters which we have studied on the growth rate of genes instability, which are the fundamental parameter. Now there are so many other parameters like flavor oscillations or like magnetic field or quantum corrections that we can study. So this is all about my talk. Let me summarize this, that in this talk, we have just basically studied the interaction between the neutrino and plasma and how they modify the fundamental waves and instabilities, how the propagation of MHD waves take place in such an environment where there is a mixing of neutrino beam with the plasma. So for that, we have used the neutrino modified MHD model. A dispersion relation is derived using the normal mode analysis, and the growth rate of the fast neutrino driven short wavelength instability is also derived. In the oblique propagation, the Jeans instability criteria was depending upon the neutrino beam, while there was no effect of the neutrino beam in the case of parallel and perpendicular propagation. In neutrino beam density is stabilized, while the free energy of neutrino beam destabilize the growth rate of Jeans instability. And this type of results are applicable to understand the formation, to understand the type of core collapse supernova, in which the Jeans time scale is comparable to the time scale of the supernova explosion. And since the time scale of neutrino beam was much shorter than the Jeans time scale, so we can expect that there is a fast mixing of the neutrino beam in the gravitating plasma. So this is all about my talk, and I once again I thank to Dr. Swarniv for giving me this opportunity and sharing my presentation. So thank you very much. Swarniv.
Yes, thank you, Dr. Prajapati. We have got some questions. Sir, am I audible?
Yes.
Yes.
Yes, yes. I
Yes.
can hear you.
Okay. The first question is from Onu Srishen. Sir, would you please explain Jeans mass? Jeans mass.
Okay, Jeans mass. Basically, Jeans mass is the mass, maximum mass cloud that it supports due to the gravitational force, and beyond this mass, there is a fragmentation. So Jeans mass is given mathematically by the order of 1.4 of the solar mass. That is, this is called the Chandrasekhar mass limit. So any gravitating matter which has this mass, it will be gravitationally stable, and beyond then this mass, there will be fragmentation occur. So Jeans mass is basically a mass of cloud which is supported by the gravitational force under the Chandrasekhar mass limit.
Okay, thank you, sir. And another question from Onu Srishen. Sir, what is the physical meaning of this growth rate? How do we determine it?
Okay. The physical meaning of growth rate is that very simple, that you know the simple wave propagation, that if we have a simple dispersion relation omega equals to CSK, so there is a linear relationship between omega and k. So in a plasma, simply there is also this kinds of waves, but when the plasma particle they get excess energy, so due to this excess energy, these linear or periodic wave, they become aperiodic or growing wave. So this growing wave turns into the instability, and their growth rate are, this is the rate basically by which we can say that how the perturbation, how the wave frequency is depending upon the wave number. So basically this growth rate tells you about that by which rate the wave is fasterly turning from aperiodic to the, from periodic to the aperiodic wave. So that is the growth rate.
Well, sir, 2 minutes. Well, we have a lot of applause. And one question from Mimi. She is asking, sir, is the mixing of neutrinos during the core collapse obey convective laws or radiative laws? Well, it's a very good question. Thank you, Mimi. I repeat the question once again.
That is a very good question.
The mixing of neutrinos during the core collapse, do they obey convective laws or radiative laws?
Basically, it is a. I think it is a convective loss, because in the radiative loss, we generally basically tell about the cooling of the plasma particles. But here we are talking about the mixing of the neutrino with the plasma particles. So I think the convective part is very important instead of radiative part. So because radiative part is considered when we talk about the collapse of, or when we talk about the formation of stars from the molecular cloud, that is from hot to cooler medium. But here the energetic neutrinos, they are involving with the plasma particles. So I think the convective part is very important as compared to the radiative one. But I'm not sure about it. I will also see this question. So it was a very interesting question. I will go through in detail of this question.
Yes.
Thank you for nice question.
Well, and Onusushan just requested, sir, could you just share your PPT if possible, so that, or the references, if it's possible to give a references.
Okay, sir. I will.
I think you can send it to me so that I can.
And actually finished before 10 times, because you can understand that I was busy in our conference schedule.
Yes.
So we have finalized, and so somehow I could get time and I presented my work.
Sure.
So anyway, thank.
And I would just like to inform everybody. I think most of the audience out here, they know it, that Prajapati sir is organizing an international conference, PTS, Plasma Technology and Simulations. So it's on 14th and 15th, isn't it?
Please you circulate in your group.
Yes, it is already circulated. I'm just, for the live audience, I will just share it. And once again, so this is one of the opportunities where you can present your work and learn new things. So speakers are there. So kindly register for that conference, and I will give you the link soon in the chat box.
Okay.
So that will be very helpful for them. And thank you once again from on.
Okay. Thank you.
Yes. Thank you, sir. Well, thank you, everybody. And thanks to Prajapati sir and all my audience students out here. So the next talk will be by Professor Dimitri Batani, and he will be just live in few minutes. Just I would just suggest all of you to be ready with your things. So I will just turn off the video and come back in few minutes. Just hold on. Thank you. Well, I've just asked the audience to be patient for a few minutes, and by the time we have a connection. Well, Professor is there. Thank you, sir. Well, a few words regarding Professor Batani. So can you just turn on your video? Good evening, sir.
Good evening. I don't see you.
Well, I turned off my video. Well, I think it's visible now.
Okay. You.
Ciao. So we have our just well, students and friends. We have Professor Dimitri Batani with us. He is presently in the University of Bordeaux, Cilia Laboratory in France. And he is a master in laser plasma interaction. And a few words about him. I would just like to thank him once again. So he's a member of the IUF Institute of Université de France from 2015, and he's a chair the Excellence Regional or the Regional Acquaintance chair holder, and he's also the honorary professor of NILO, Pakistan, as well as honorary professor of Jadavpur University. So it's a long time that we know him from his works and also as a person. Thank you, sir, because we have met quite a few times. So before joining the University of Bordeaux in 2015 as professor, he was an associate professor in the University of Milan, Bicocca from 2005. I apologize for the pronunciation. And from September 2004 to February 2005, and he was a visiting professor of École Polytechnique Bilaspur in Paris. So before that, he was with the University of Milan again, and in 1992, he was a senior researcher in the Milan University, and he did his oh God, you have such a huge experience, sir. Thank you. It's just mesmerizing. But your work is more interesting than anything, I would say, because it's highly intense laser things. Because these students, they have been studying intense laser interactions theoretically, but as an experimental point of view, I think you will enlighten them and give them some motivation to carry out research in intense laser plasma interactions towards inertial confinement fusion. So today we have one of his talk, and tomorrow also at the same time we have him with another topic. So the title of his talk today is The Fusion in the Universe and in the Laboratory, and tomorrow the title of his talk is Advances in Inertial Confinement Fusion. So both these talks are very much interesting for students as well as from the academic point of view. Thank you, sir. Please.
So thank you very much for your nice and very kind introduction. I would like to say that it is a pleasure to be virtually present in Kolkata again. Of course, I would like better to be there in person, but due to the present situation, this is a bit difficult. But I hope that I can visit India again soon. So, as you have listened, I have two talks. And the talk of today is more a general introduction, let's say more at the level of bachelor students or first year of master. And tomorrow I will instead speak in detail about inertial confinement fusion, which is really the subject of my work. And that will be a bit more technically detailed. So I open my presentation and I share my screen. Just tell me if you see the presentation. Can you see the presentation?
No, sir, not yet.
Maybe I forgot to do something. Wait. So I go back to Zoom. Yes.
Yes.
Okay. So actually, I forgot to share my screen. Sorry.
Yes, thank you. Yes, sir. It is visible. Thank you, sir.
Okay. So let me go to the presentation mode. Okay. So wait. Sorry. Okay. So this is the talk of today: fusion in the universe and in the laboratory. So I I would like to start with some historical perspective. Let's say that the voyage of nuclear fusion started about 8 years ago. This was after the end of the Second World War, and it was after the invention of the hydrogen bomb. You may know that atomic weapons, conventional atomic weapons, let's say, are based on fission of uranium or plutonium, while the hydrogen bomb is based on the fusion of hydrogen. And this is, of course, much more powerful than the fission devices. So actually, about 8 years ago, the fusion weapons were demonstrated. And after this, the same scientists which contributed to development of this weapon thought that it could also be possible to use fusion, controlled fusion, for production of energy for mankind. So actually the names which are at the beginning of this trip are names like Sakharov and Teller, who are indeed the same person who were deeply involved in the construction of the hydrogen bomb in the Soviet Union and in the United States, respectively. So at the time, they were very optimistic. They said maybe in 20, 30 years, we will have power plants based on fusion. And indeed, despite much progress which has been done in fusion, the research has also provided many disillusions. And today we still do not have power plants working on nuclear fusion. Then the next step is 60 years ago, the laser was invented. And this opened the field of inertial confinement fusion, on which we will speak tomorrow. And again, the names are like Basov, who is one of the winner of the Nobel Prize for the invention of the laser, and other person like Nucleus at the Lawrence Livermore National Laboratory in the USA. Now, today we are still facing great difficulties to demonstrate fusion, controlled fusion in the laboratory, but I would say that we are also probably very close to the demonstration of ignition, which is the scientific feasibility of fusion in the laboratory, which will conclude the first part of this travel. Of course, there will be still a lot of work to do, because once you have demonstrated that nuclear fusion works in the laboratory, then you still have to solve all the technological problems and to build power plants. So this is the plan of my talk. Today I will speak about what is nuclear fusion, how nuclear fusion works in star, and the research mainly on magnetic confinement devices on Earth. And tomorrow we will speak about inertial confinement fusion. So I will start very, very simple. Forgive me if I tell you things that you already know, but it is just to remind and to build a common language. So of course, you know that in the nucleus of the atom, you have protons and neutrons, and protons are positively charged, so they try to repel each other. So the Coulomb force, the electrical force, tries to bring the proton apart, tries to break the nucleus. The neutrons are not sensitive to electrical force because their charge is 0. On the other side, you have the nuclear forces, and actually the nucleus can be stable because the nuclear force, which acts both on protons and neutrons, is bigger than the electrical force. And of course, you realize now that neutrons have a stabilizing effect on the nucleus because they contribute to bring the nucleus together by nuclear forces, but they are not sensitive to repulsion electrical forces. Well, again, nuclear force is stronger than electromagnetic force, but it is short range. Electrical force is weaker, but it is long range. When we speak about short range, is really the dimension of the atomic nucleus. Actually, the dimension of the nucleus is defined by the range of the nuclear forces. So if you have two nuclei and you bring very close to each other, I mean, you really put them in contact with each other, they they will fuse together because the nuclear attraction wins. But as soon as they are far, the electrical repulsion wins, and they will try to go even more far apart. And of course, you realize that if this was not the case, our universe could not exist as we know. If nuclear force was also long range, it would win against electrical repulsion at any distance, so everything would collapse. On the contrary, if electrical force was as strong as nuclear forces, no nuclei could form. Actually, this is a rough scheme of the potential energy as a function of distance. So you see, the nuclear force here is represented as a potential well, and then you have the 1/r potential energy related to the Coulomb force. So you see, if you bring two nuclei together close enough, they will merge. And actually, what I said before is not completely correct. I mean, in many cases, you do not really need to touch the two nuclei touch each other. They can even fuse at a very short distance, thanks to the tunnel effect, which is very well known in quantum mechanics. So let's say if 0 is the position of the first nuclei, if you bring it here, of course they will fuse. But they have a significant probability of fusing, even if you bring it here, because it will tunnel through the potential barrier. And of course, if it is more distance, then the electrical force will win and it will be repelled. So when you put the two nuclei close enough, they will fuse, they will make a bigger nucleus, and this nuclear fusion reaction may release a big amount of energy. Well, whether it releases the energy and how much energy release depends on this graph here. These represent the average nucleon binding energy in the nucleus. That is the energy that you have to provide to the nucleus to be able to extract one proton or one neutron. And these are the experimental data which are well reproduced by the formula from this German scientist, von Weizsäcker. So if we look at this graph, there are different regions. The heavy elements, like uranium, for instance, they can break. This is the process of nuclear fission. And when they break, the average the binding energy increases, which means that some energy is released. So you break uranium-238, for instance, you will create nuclei with the Z number, A number around 118, and you will release energy which is typically 1 MeV. On the other side, the light elements, they release energy in fusion reaction. So if you have H2, deuterium, and you fuse two deuterium nuclei to make a helium nuclei, you can release a big amount of energy. In this case, the energy is 6 MeV. So actually, the energy released in nuclear fusion is bigger than the energy released in nuclear fission. And then you have the third region in this graph, which is around the maximum, which corresponds to iron. And these elements are very stable because you do not get energy when you fuse them, and you do not get energy when you break them. And we will see that this is also very important for the models for the physics of the stars. Well, this energy, which is released, actually comes from a mass difference. For instance, if you have deuterium and tritium, which are two isotopes of the hydrogen, and you fuse them, in the end, you get one neutron and one helium nuclei. And these final elements are less heavy than the initial elements. So the difference of mass is converted to energy using the well-known Einstein formula. And now, and now, again, this is the zoom of the previous graph, and you see that helium-4 has a very high binding energy, which means that if you go from deuterium to helium, or from tritium or helium-3 to helium, you have a very big energy gain per nucleon. Of course, there are 4 nucleons in helium, so the total binding energy will be about 28 MeV. So it means that whenever helium is the final product of the fusion reaction, you get a maximum release of energy. Well, actually, nuclear fusion is mainly related to the names of many physicists, and one very important one is Hans Bethe, who was a German physicist who escaped the Nazi government in Germany and became American. And he was the one who in the 1939 understood that the source of energy in the stars is related to nuclear fusion. Before, I mean, it was not very clear why the stars are bright and why they provide energy to us, for instance. It was only thanks to the theory of Bethe that the process of energy released in the stars was clarified. And actually, his theory is also very important because it is the basis of what we call the nucleogenesis. That is the theory of how all the different atomic elements in the universe are formed, starting from hydrogen. Well, just to give you a number, in the sun, every second, 4 million tons of mass are lost. And these are converted to energy. So every second, our sun reduces its mass of 4 million tons. And the process is the fusion of hydrogen, which brings to helium. Well, of course, you understand that there is a problem here, because here you have 4 protons, and in helium you only have 2 protons and 2 neutrons. So this reaction involves the transformation of 2 protons into 2 neutrons, which is possible thanks to the inverse beta decay. That is, the proton emits a positron, which is the positive twin of the electron, and becomes a neutron. Actually, the chain of fusion reaction in the stars is quite complicated. This is actually the contribution of Bethe to the study of nuclear fusion in the star. You start with hydrogen. Hydrogen, 2 protons, 2 nuclei of hydrogen will fuse to produce a deuterium. Then deuterium will fuse with hydrogen to produce helium-3. And finally, 2 helium-3 will fuse to produce, again, free hydrogen and the nuclei of helium, which is also called an alpha particle. Actually, this is the chain of reaction which works in the stars which have the dimension of our sun or smaller. If the star is bigger, then the chain of reaction is even more complicated. But I mean, for the goals of this lecture, we will stop just with this chain reaction. And now it is important to understand that the stars are systems in dynamical equilibrium. On one side, you have the gravitational force, which is attractive, and so it will try to cause the implosion of the stars. And this force is counterbalanced by the energy released by the nuclear fusion taking place in the center of the star, mainly in the center of the star. And this acts as a radiation pressure which keeps the star stable against the gravitational force. So now we can understand a bit of the history of stars. Initially, the stars are made of hydrogen, and they burn. By burn, we mean they do nuclear fusion reaction. They burn hydrogen to produce helium. This is the case of our sun, for instance. But as time goes by, hydrogen will reduce, will finish. So the star will become richer and richer in helium. This means that you will have less and less nuclear fusion reaction. So the radiation pressure will not be strong enough to win against the gravitational force. So when the hydrogen tends to finish, the gravitational force will win, and the star will reduce its size. By reducing its size, the density and the temperature of the star will become bigger. And in this condition, you can trigger another process, which is the fusion of helium. So helium, two nuclei of helium will fuse to produce a nucleus of carbon or oxygen. So in this phase, you have a star which is burning helium. Then this cycle will repeat it again and again. When helium is reduced, the nuclear fusion reaction will be less and less. The star will contract again, and at that time, carbon nuclei will begin to fuse to produce neon and magnesium. And oxygen nuclei will fuse to produce silicon and sulfur. And then it will happen again. And at the given time, silicon and sulfur will fuse to produce iron. And then at this point, there is a catastrophe. Because if we remember this graph here, the fusion of iron does not release energy. So it cannot produce net energy, it cannot produce radiation pressure. So when the star reaches this level in which silicon and sulfur fuse to produce iron, the radiation pressure stops. At this time, nothing can win against the nuclear forces, against the gravitational forces. So the star will collapse in a catastrophic way. And then because of this implosion, it will explode. And this is a supernova. Well, all these take place if the star is big enough. Because if the star is small, it will, by contracting, it will not be able to reach the condition of temperature and density, which are enough, for instance, to start the carbon fusion. But if we consider a big star, sorry, this view graph is in French, but I think that you can really understand very well. If you consider a big star, at the beginning, it will burn hydrogen. The typical temperature will be something like 40 million degrees. And this phase of hydrogen burning can last several million years. For helium, the temperature and the density will increase, and the phase will be much shorter. And then for carbon and oxygen, you see, will be 600 years and only 6 months. And then the final phase of fusion of silicium to produce iron will only be 1 day. At this time, the star will collapse in less than 1 second, and the rebound of this collapse will produce the explosion in a few milliseconds. And this is an image of the Crab Nebula, which was formed by the supernova explosion in 1054, which is important because it was recorded by Chinese astronomer at the time. So it is the first historical recording of a supernova explosion. Well, as I said before, if the mass of the star is too small, when it contracts, it will not be able to reach a temperature high enough to trigger the fusion reaction of heavier elements like carbon and oxygen. So this star will contract until when the pressure of the degenerate electrons will balance gravity, and this will be a white dwarf rich in carbon and oxygen. So this star do not really have a source of energy because there are no longer fusion reaction. And this star becomes colder and colder as it continues to radiate. And there are hundreds of white dwarfs in our galaxy. So this is, let's say, a summary of stellar evolution, which depends on the mass. So if you have the mass of the star, which is about very small, 7% of the mass of our star, the temperature in the center will never be enough to trigger hydrogen fusion. So this is not a real star. It is like an aborted star. It's like a giant Jupiter. It is called the brown dwarf. Then you have the sun, the stars which are about the size of our sun, between 7% of our sun and 8 times our sun. So these stars burn hydrogen. Actually, they burn hydrogen in a much slower way as compared to big stars. And once they have finished to burn hydrogen, they will burn helium. But then they will not be able to trigger the fusion of carbon. So helium will fuse in carbon, and there the process finishes. So the star will become a white dwarf rich in carbon and oxygen. If the star is bigger than about 8 times the mass of the sun, you have the fusion of hydrogen, helium, and after carbon, oxygen. And then the star will become a red supergiant, as I show in this scheme, is this plot here. And at the end, it will explode as a supernova. And then what happens after the supernova explosion? Well, if the mass is below 25 times the mass of the star, the residual of the supernova will produce a neutron star. But if the mass, the remaining mass after the supernova explosion is bigger, then you will get a black hole. So you see that basically fusion as the source of the radiation pressure and the mass of the star decide the whole destiny of the star. And basically this view of stellar evolution is connected to the name, to a name that you certainly know, that is Chandrasekhar, who is a very famous Indian physicist. Now, this is what is happening in the star. So what happens now in the laboratory? What we are trying to do on Earth? Well, we are using isotopes of hydrogen. We use deuterium, which is the isotope of hydrogen with 1 neutron in the nucleus, and we use tritium, which has 1 proton and 2 neutrons. And why we use this DT, we try to use this DT fusion instead of the 4-proton fusion that works in star? Well, basically, the answer is simple. This one is a one-step process. You directly fuse deuterium and tritium to get alpha particle and neutron. This, as you have seen, it's a multi-step process. So if you calculate the probability of this process and the probability of this process, you will see that this one is 10 to the 25 times more probable than this chain of reaction. So basically, this one works very well in stars because in stars are big and stars last for many million years. So the product of this this first reaction, they have the time to meet other particles and fuse again. But on Earth, this will be very, very difficult. So there are many fusion reactions, and in reality, research is focusing mainly on the deuterium-tritium fusion reaction. You have deuterium, which fuse with tritium and release 1 alpha particle and 1 neutron, plus 17.6 mega electron volt. So why do we study mainly this reaction? Well, the answer is that this is the easiest to be obtained. If you make a graph of the cross-section, which is the intrinsic probability of a nuclear fusion reaction, and you compare this one with other fusion reaction like deuterium to helium-3 or deuterium to deuterium, you see that the DT fusion reaction has 2 characteristics. First, it has a much bigger probability. You see this peak is much bigger than this one or this one. And second, the energy corresponding to this peak is much lower, which means that in order to fuse the deuterium and the tritium, you must provide much less energy to the system. Maybe let me just go back a second to this graph here. Again, if you have particles which have some initial kinetic energy, they will approach each other. They will slow down because of the repulsion due to electric forces. And when the initial kinetic energy becomes equal to the potential energy, they will stop. And then they will be reflected. So the bigger the energy, the closer they will go to each other. So you need to give very big energy to these nuclei if you want them to fuse. But you see that the energy which you need to provide to the deuterium and tritium is much smaller than the energy that you need to provide to other particles. Here you have 100 keV against 400 keV or 1 MeV. So this is the nuclear fusion reaction. Deuterium and tritium fuse. They will produce an unstable helium-5 nuclei, which will split in an alpha particle and a nucleus. Well, and as I said just now, in order to bring deuterium and tritium close enough, they will need to have high velocity, high initial kinetic energy. But from the statistic statistical mechanics point of view, high velocity means high temperature, which means that you have a mixture of deuterium and tritium, and you must bring it to a temperature, a minimum temperature of the order of 5 to 10 keV. And let's remind that 1 electron volt is 10 to the 4 Kelvin. So we are speaking about 10 keV is 10 to the 4 electron volt, so it's 10 to the 8 Kelvin, is 100 million Kelvin. And of course, at such temperatures, atoms are ionized and matter becomes a plasma. So the first condition to get nuclear fusion is that you are able to give a high velocity to these nuclei, which means that you are able to heat the deuterium-tritium fuel to a very high temperature. But this is not enough in reality, because in order to have production of energy, you have to have many fusion reactions, which means that you have to have many ions and you must keep them together for a long time enough. This is called confinement time. And there is a criterion which is called Lawson criterion, which states that the density of the ions, which is the same as the electronic density because we are dealing with hydrogen, times the confinement time must be at least 1.5 10 to the 14 second per cubic centimeter. So this summarizes the condition to make effective nuclear fusion in the laboratory: high temperature and a high product of density and confinement time. And as I said, at this high temperature, matter becomes a plasma, which means that it is ionized. So, how can we make fusion? Well, the first way is gravitational confinement, which works in stars. The second way is by magnetic confinement. We will look at it a bit later today. And in this case, the density of the plasma is rather low. It is about 10 to the 14 particles per cubic centimeter. And the confinement time is big. It is of the order of seconds. And then the third approach is inertial confinement time, inertial confinement fusion. In this case, the density is very big, but the confinement time is very small, less than 1 nanosecond, 10 to the minus 9 seconds. So you see, in gravitational confinement, you have big density and big confinement time. And this works very well in stars. But on Earth, we are not able to get at the same time a big confinement time and a big density. So we can either get big confinement time and low density, and this is the magnetic confinement, or we can get big density and short confinement time, and this is inertial confinement fusion. Well, once, if you suppose that you are able to produce energy by nuclear fusion, then the power plant, in a way, will be quite conventional. Well, with some very detailed characteristics, but basically, the energy which is released by the plasma will be absorbed in a heat exchanger and will produce water vapor, which will be produced to make a turbine rotate and to produce electricity as in a normal coal or nuclear power plant. Well, the detailed characteristics of the nuclear or the fusion power plant are related to the presence are related to, first of all, to the presence of this lithium mantle. Well, this lithium mantle is needed because deuterium is an element which exists in nature, is very, very abundant, but tritium is a radioactive element. The lifetime is only 12 years. So tritium must be produced. And actually it is produced, it is produced in this lithium mantle by absorption of neutrons. So neutron plus lithium produce again helium and tritium. And it releases energy also. So it contributes to the net power balance of the nuclear plant. Well, the second characteristic of this power plant will be that you need a very efficient heat exchanger. So probably you will need a liquid metal exchanger as it is similar to the case of a fast breeder fission reactors. Well, I spoke about these three approaches to nuclear fusion, and of course there is the other approach, which is uncontrolled, which is the H-bomb. And in this case, you can get relatively high confinement time and relatively high densities because you have a lot of energy which is provided by the primary system, which is a conventional nuclear bomb. And of course, this shows you two things, that for controlled nuclear fusion to work, of course, you need to ignite with a different tool, so magnetic field, laser, and so on. But you also need to ignite a very small mass of thermonuclear fuel, because if this mass is big, the release of energy will be very big, and it can be like an explosion. So let's speak about magnetic confinement. We have to confine the particles in a volume in order to satisfy the Lawson criterion. So how can we confine the particles? Actually, we cannot put them in the box, because if we put in the box, they will collide with the walls of the box with two effects. First, they will cool down, which is not what we want. And second, the release of heat to the box will destroy the box because the very high temperature of the material. So you need to have other tools to confine the plasma. And one tool is, of course, the magnetic field. Because you know that if you have an electron or an ion which has some velocity in a magnetic field, there is a force which is acting on this charged particle, which is the Lorentz force, which is perpendicular to the magnetic field and to the velocity. So it will be directed in this way. So as the particle moves, the force will always be directed inward. So the final result is that the particle will move in a circle around the line of force of the magnetic field. So basically, this is the idea. If you have a plasma without magnetic fields, the particle go everywhere, because it's just like a gas. There is absolute chaos. But if you have a magnetic field, the particles are obliged to move in circles around the field line of the magnetic field. So the magnetic field confines the particles in the transversal direction. The particles cannot go in this direction because they are obliged to move along the force line. Well, this solves the problem of confinement in one direction, but of course in the other direction, along the line of force, there is no confinement. So the problem is how to try to get confinement in 3D. Well, the first idea was to use the so-called mirror machine. In the mirror machine, you have a magnetic field which is not uniform, but is, let's say, weaker in the middle and stronger at the edges. And now, if you study the dynamics of the charged particles in this magnetic field, you will discover that there is what is called the mirror effect. That is, as the particle approaches the region where the force lines are closer to each other, which is the region where the magnetic field is stronger, the parallel velocity, the velocity along the field line, will decrease. So depending on the initial value of this velocity, the particle will decrease its velocity, and at a given time, it can stop. The velocity becomes zero. And at this time, the particle will be reflected. So in this case, because of this mirror effect, you have a confinement along the parallel, in direction parallel to the field lines. Well, this is a big step, but in reality it's not enough, because the particles which have a big energy, they will not reduce the velocity down to zero, and they will be able to escape. So there is an improvement in confinement, but it's not enough. So the idea was maybe we can close the field line in a toroidal geometry. So in this case, the particles will move along the line force of the magnetic field, and they will be confined to this torus forever, let's say. Well, again, this is a very big step, but it's not, again, is not sufficient, because there are some other phenomena which implies that with time, particles are lost. And in order to avoid this loss of particle, you have to produce a new geometry, which is a mix of toroidal and poloidal configuration. So it means, in addition to this toroidal field, you have to have some poloidal component. So the toroidal field is along the cylinder, let's say, and then you close the cylinder, and the poloidal is perpendicular to the cylinder. If you have this poloidal field in addition to the magnetic field, to the toroidal field, you will get a configuration like this, in which the force, the line of force of the magnetic field turn around this donut. And this helps the confinement quite a lot, because it brings the particles which are on the outside, which are the particles which will try to escape, it brings them back again to the inside. So this configuration is called a tokamak. The tokamak was invented at the Kurchatov Institute in Moscow in 1950 by Andrei Sakharov and Igor Tam, both of them Nobel Prize winners. And tokamak comes from the Russian, of course, which means toroidal chamber with magnetic coils. And basically, what is the idea of the tokamak? The idea of the tokamak is that you have these coils which produce the toroidal field, and then you have the plasma inside. And if this plasma is in motion, there is a current, it will produce a poloidal field. So the external magnetic field plus the poloidal field produced by the plasma will produce this tokamak configuration. Well, and how do you produce this plasma current? Basically, you consider, you create a transformer. You have a classical transformer where the secondary circuit is the plasma itself. So by circulating a big current here, you induce a current in the plasma, which means that the plasma will move and will produce the poloidal magnetic fields. So this is an example of a tokamak. Actually, it is the biggest tokamak which is now working, which is the JET, the Joint European Torus. It is a project of the European Union, and it is working in Calais in the UK. And you see what is the size of this toroidal chamber. Again, these were some images related to the construction of the jet. These are the coils to produce the toroidal fields, and these are the arms of the transformer, which is producing the poloidal field through the plasma. Again, this is an image of the internal chamber. Initially, the wall of this internal chamber were made with graphite, and then they've been replaced with beryllium. Basically, you always want to use low Z elements, because if they go to the plasma, they will not radiate too much. So they will not contribute to cooling down the plasma. And again, this is an image of the internal chamber of the jet. And this is the jet with the plasma. Okay, the plasma is transparent, so you can just see some light. Now, what is the next step in magnetic confinement fusion? It is what is called ITER, International Thermonuclear Experimental Reactor. This is an international project. Actually, the original idea of this project came out when Gorbachev and Reagan met in November 95 in Switzerland. This was a discussion to reduce atomic weapons, in particular to reduce fusion atomic weapons. And let's say that as a corollary of this proposal, they also thought about research for controlled nuclear fusion. This reactor is now in construction in Cadarache in the south of France, near Marseille. This is the size of ITER, so actually it will be much bigger than JET. You see, this was JET, and you can see the size of the person here. And this is ITER, and you see the size of the person. And ITER is an international project which involves the European Union, Russia, India, United States, Korea, Japan, and China. The cost of this machine is about, well, it's difficult to estimate in reality, but it's more than 20 billion euros or dollars, if you want. And the construction is expected to be finished by 2025. Well, there is another approach to magnetic confinement fusion, which is called the stellarator. Well, the main idea, again, is how to get the poloidal field. In tokamak, you get the poloidal field by the plasma current. But actually, you could think about making coils with some special shape, which produce at the same time toroidal and poloidal field. So you will not need, in this case, plasma current. And, well, you see that this is absolutely complicated. I mean, the coils of a tokamak are just simple coils. Maybe they are ellipsoidal or D-shaped, but I mean, they are all the same. And this is a very complex 3D structure. You see, again, the shape of these coils. Now, the big stellarator which is now operational, is the so-called Van der Stein 7X, which is working in Germany. And if we want to make a comparison between tokamak and stellarator, well, this is based on plasma currents. Here there is no need for plasma currents. Here you have simple coils. Here the coils are very, very difficult. Here you have a limited discharge duration because you have a transformer. So the plasma is set in motion by the variation of the current in the primary circuit. And of course, if you have a limited maximum current that you can drive, you have a limited maximum duration between 0 and the maximum of this current. So stellarator can in principle be continuous machine. Tokamak are pulsed machine. You have to make a discharge, then make another one and another one. So in this case, the plasma is stable. In this case, you can have a lot of plasma instabilities which are produced by this current. And this is actually the main problem of tokamak in these days. How to kill the instabilities which prevent reaching the temperature which is needed for fusion reaction. Well, today, tokamaks are much more advanced than stellarators. Indeed, JET has already produced a record output energy, output power from fusion reaction of 16 megawatt, and ITER is predicted to provide 500 megawatts. Here, for the moment, no deuterium plasma, no deuterium tritium plasma has been used yet. So this is an approach, let's say, that started later. It got some delay, but it is a backup solution in case ITER will not be able to work. And actually, here are again the inventors, sorry for the quality of this picture. These are again the inventor of the tokamak, Sakharov and Tam. And this is the inventor of the stellarator, Lyman Spitzer, which is again a very well known in plasma physics. And then we have the alternative approach, which is inertial confinement fusion. And I will finish here for today's lesson. The idea of the inertial confinement fusion is completely different. You take a small sphere of cryogenic DT, you take a deuterium tritium ice, you shine this sphere with laser so that you get the sphere to implode, and by implosion you increase the density and you increase the temperature until you reach the condition for nuclear fusion. And if you are able to produce the condition for nuclear fusion, then you will get a micro explosion. So you will get basically a sort of hydrogen bomb on a microscopic scale. And this will be the subject of tomorrow's lesson. So for the moment, thank you very much for your attention. And I'm open for questions if you have any.
Thank you, sir. It was so summarizing. Basically, all those ideas which are important these days. Basically, we have fusion reactors here, fission reactors. But regarding fusion and ITER, all these undergraduate and first years of postgraduate students, they have a bit vague idea, majority of them. So your talk was helpful for them. Right now, I would ask the students if they have any queries to kindly put your queries in the chat box so that I can convey it to sir. But sir, just a minute.
Sorry.
Yes. No.
I don't see you.
Oh, I haven't turned on my video.
Okay.
Okay, sir. You have some questions. Suman is asking, sir, to hold the magnetically confined plasma for such a huge heated chamber, they must need huge magnetic field and superconductors to make those huge magnetic fields. Is it so? Is the first question.
Yes, you need a very huge magnetic field. I mean, you need to have magnetic field which are of the order of 10 Tesla or even more. Now, making 10 Tesla in a small volume nowadays is not too difficult, but making 10 Tesla in the volume of ether, this is still a very big problem. And they are using superconductor magnets because, of course, you need to produce, you need high currents to produce strong magnetic fields, but you need to have low production of power, of heat. So basically you need superconducting, which means that you need a big circuit also for helium, for cryogenic helium to cool everything down. Actually, I don't know who is producing them. There are many, in the ITER project, many parts are produced by different countries. So you see, there are some parts which are produced in Japan, some part in Europe, some part in India, and so on. And then everything is brought to Cadarache in France and put together. Okay, I cannot tell you who is producing these coils, but for sure it is a huge technical achievement.
I think the IPR, Institute of Plasma Research in Gandhinagar in India, they have an ITER branch, ITER India project. So they supply part of the equipments and some machineries. Yeah. And another question, sir, from Mimi, how is the related to stellar fusion? How the metallicity of a star being very light in comparison with that of majority of the composition of the entire star affect the evolution of the fusion? Does it really affect the fusion until
can you repeat the question, please? Sorry, can you repeat the question?
Yes, yes. How the metallicity of a star affect the evolution of the fusion? Does it affect the fusion until the temperature gets high enough to make it effective?
Okay, I'm not really an expert in astrophysics, but let's say that metals, the presence of metals in the star is very important because it affects quite a lot one property which is called the opacity of the plasma, the opacity of the star, which means how the materials absorbs the X-rays and re-emit the X-rays. So basically, you have this nuclear fusion which produce energies. But then in reality, all this energy in the end is converted into radiation. In particular, is converted into X-ray radiation. And this is actually the radiation pressure. Let's say the nuclear fusion does not provide directly the radiation pressure. It is the indirect source of this radiation pressure, but the real carrier of the radiation pressure are X-ray photons. And the metals, they tend to have a very large absorption of X-rays. I mean, if you have pure hydrogen plasma, the absorption is very poor, okay? But as soon as you have some impurities, the absorption and the emission increase quite a lot. Actually, this is a problem in controlled nuclear fusion too. If you have a pure plasma, the emission will be small. But as soon as you have impurities, like metal impurities, the plasma will radiate quite a lot and it will become cool. And that is why in jet, for instance, you have a beryllium wall. Sorry.
Okay.
So
I think that is
the presence of the metal is very important in deciding the evolution of the star. And actually, until now, we do not fully understand the structure of even our sun, because there have been recent measurements of the opacity of iron, which show that the opacity of iron in the sun is quite different from what we use in the models. So just to conclude, the metallicity is very important because it affects the radiation pressure. And of course, it changes during the evolution of the star.
Well, the students have liked quite a bit, so much of applause. So I think tomorrow's talk on inertial confinement fusion will be technically interesting for them, because it is a very recent topic. And yeah, well, one more question, sir. Some Sharon Ghosh asked, sir, from plasma, can we get a gas or another lower temperature state, just like gas to liquid?
Okay, plasma is just a state of matter. So you can get a transformation of solid to liquid, liquid to gas, gas to plasma. This is just the usual path. But in reality, you can have more than this. In some condition, you can directly go from solid to plasma. And you can make the inverse transformation. All this depends by the phase diagram. Sorry.
It's okay.
All this depends by the phase diagram of the material. So the natural approach is that if you have a plasma and you let it cool down, it will go to a gas, and then to a liquid and to a solid.
This is the last question which we will be asking. For nuclear reactor, they propose trash, which are harmful for nature. What about ITER? Does they produce trash also? No, nuclear waste, I think no, because it's a fusion.
Okay, this is a very important question. There are two types of radioactive waste. The first type is directly related to the process. You know, for instance, if you have nuclear fission, you break uranium or you break plutonium, and you get elements which are in the fuel bar, which are the waste, the radioactive waste. And this radioactive waste, which directly comes from the process of fusion, they might have 100,000 years of half-life. And then there is the second type of radioactive waste, which comes from the activation of the material of the reactor. So in this case, you have the reactor, which is maybe iron, steel, and the neutrons, which are released by fission or by fusion, are captured by the atoms of the chamber. And this neutron capture can change the atom to a new atom, which is radioactive. So in this case, you have this secondary radioactive waste, which, let's say, in a way can be controlled. If you carefully choose the material, you can have activation, which will produce radioactive waste, which will not have a lifetime of 100,000 years, but maybe which will have a lifetime of only 100 years. So in a fission reactor, you have the two types of nuclear waste. In a fusion reactor, you only have the nuclear waste, which comes from the activation of the material, because the nuclear fusion itself does not produce radioactive material. You have deuterium and tritium, and in the end you have helium, which is stable. The only source of waste is by the neutrons, which are produced in the nuclear fusion, which are captured by the reactor, by the materials of the reactor. So, for instance, when you design a fusion reactor, you must be very careful in avoiding certain types of atoms which can produce long life waste. For instance, you will try to avoid the use of iron. Maybe it's better to use aluminium, something like that. So let's say that a future nuclear reactor is not completely clean, but it is much cleaner than a fission power plant. And of course, in the far future, we will maybe able to use other fusion reaction like proton boron. Proton boron produce the fusion reaction of hydrogen and boron produce no neutrons, it only produces alpha particles. And in this case, even the activation problem will be solved. But this, at the moment, is really just like science fiction, let's say.
Thank you, sir. So,
thank you very much to you. We see each other tomorrow.
So tomorrow we'll be having you once again with us, and tomorrow's title of the topic is on inertial confinement fusion. And students, please go through initial understanding or initial literature so that you can understand sir's talk very well. And as like today, we will cover from the basics and like his usual way, mesmerizing style. So I think, sir, your talk was wonderful today.
Thank you very much. Okay. Bye. See you tomorrow.
Sure. Thanks. Parveen Kaur. So she is our next presenter. Parveen Kaur is from GNDU and she is a student participant out here. And today her talk will be the last talk. And before we come a bit, let me tell you something about tomorrow's topics, as that you students and listeners who are interested in initial confinement fusion and some alternative new kind of energy without any natural pollution, I would suggest you stress on nuclear fusion technology, because that's the need of the time. And as for India, India has been an we have done an advancement in the nuclear fusion studies research. The Bhabha Atomic Research Center, IPR, and another institutions of repute have research groups who are working on fusion, both theoretically and experimentally. And 2 days back, when we had, yesterday only, we had Professor Prasad from Ararcat, whose work is also towards laser plasma interaction. So I think these talks will help you a lot. And this workshop and the webinar series is just to get you motivated, and I can find the response very well from you students. And Parveen Kaur, will you just come live?
Okay, good evening, sir.
Okay, just turn on your video.
Okay, can you hear me?
Yes, I can hear you very well.
Okay.
Everyone.
All right, sir. So
Parveen
let
Kaur
me
is
share.
from Guru Nanak Dev University. She is a master's student, and she worked with her group. And this work is the outcome of the summer workshop on plasma physics. So,
okay.
Parveen.
Shall I start?
Yes, you may start.
Okay,
And
good evening,
introduce,
yes,
introduce yourself and acknowledge your group.
yes, sure, sir.
Okay.
Good evening, one and all who present here. This is Parveen Kaur, and I'm Bachelor of Science and Physics. Currently, I am pursuing my master's degree from Guru Nanak Dev University, Amritsar. I have not shown name of my teammates here because I have created this presentation in hurry. So I will, of course, will thank to them later. First and foremost, before starting my presentation, I would like to thank to Dr. Swarniv Chandra for giving me this opportunity to present my work. And of course, secondly, I would like to thank all the teammates, Rajneesh, Rabia, Prinkle, and Divyanshi, who cooperated me throughout the journey. So my title is Evolutionary Equation of Plasma Waves in Dispersive Medium at a Critical Regime. I will explain this topic in the end of the presentation, because after getting result, the title is come so. So I know that it is very boring to start with the definition of plasma, as we are hearing everything about the plasma, properties of plasma, collective behavior, and debate length, everything from the last few days. So that's why I will not go in the depth. So, but still I would like to highlight a beautiful point which also surprised me. Here you can see that plasma is produced when the temperature is very, very high. When the temperature is 100,000 degrees Celsius, when thermal energy becomes so high. This really surprising, as we cannot find this situation on the Earth. But of course, sun is a beautiful example of plasma. And you know, this energy is sufficient to knock out electrons from the atoms to make plasma. And now let's move toward the next slide, because I would like to highlight shock waves here. In shock waves in physics, basically it is a type of propagating disturbance that moves faster than local speed of sound in the medium. Like an ordinary wave, a shock wave carry energy and can propagate through the medium, but is characterized by an abrupt and nearly continuous change in pressure, temperature, and the density of the medium. Uh, when plane fly in the sky, we hear some kind of sounds, right? So those are basically shock waves. But here in plasma physics, shock waves are a bit different. We can explain in a different way. Here I can say that one of the dominant sources of the cosmic rays, charged particles from the space whose energies can exceed 10 raised to power 20 electron volt. Shock waves are shock waves in plasma, space plasma. So these supersonic waves are produced by supernova and other explosive phenomena in the universe. And the collective behavior, which we are listening or hearing from the last few days, the collective behavior allow a small number of particles to be accelerated to enormous energy, far beyond the reach of human-made particle accelerators. Um, so these are basically shock waves. Here I am highlighting these shock waves because my result of evolutionary equations represent shocks. I will show that later. So where we can find plasma? Here I have collected few information that the natural plasma, basically examples are sun and stars, space between galaxies, and also there are some artificial plasma which it can be produced on the earth itself in the laboratory. It can be created by ionization of gas. And plasma at a low temperature is hard to maintain because outside a vacuum, and low temperature plasma react rapidly with any molecules it encounters. And another one is the layer that is known as ionosphere. We heard about it. That is a tertiary example of the example of plasma. And the next slide, I can have collected some of the examples. Astrophysical plasma, such as all stars, solar winds, interstellar nebula, space between planets, star systems, and galaxies. And here are such as lightning bolt, auroras, ionosphere, extremely hot flames are example which come under the terrestrial plasma. And we are recently coming new technology in the market, such as plasma TVs, fluorescent lighting, plasma torch for cutting and welding, are all come under the category of artificial, or I can say, which make use of artificial plasma. So before moving ahead, it is very important to distinguish between the classical plasma versus quantum plasma, because I am dealing with the quantum plasma. So let me throw light here. What is the difference? The difference lies between the range of density and temperature. In case of classical plasma, we deal with the plasma which is which is having low density and the temperature is so high. But in case of quantum plasma, density is so high and temperature is low. And under this condition, what happens when the density is so high, de Broglie wavelength of electrons become comparable to the interparticle distance of the particles. And due to the overlapping of wave function, it gives rise to quantum effect. So this is how quantum effect come into the picture and start showing its influence when the density is so high. So let's study about the waves in plasma. Uh, when I was studying about the waves in plasma, or when I started studying about plasma physics, I realized that the waves in plasma depend upon the nature of the plasma, like its density, temperature, and pressure, and of course, the speed of the constituent. So here I can read that in plasma physics, wave in plasmas are an interconnected set of particles and fields which propagate in a periodically repeating fashion. A plasma is a quasi-neutral electrical conductive fluid. In simplest case, it is composed of electrons and a single species of positive ions, but it may also contain multiple ion species, including negative ion as well as neutral particles. Due to its electrical conductivity, plasma couples to electric and magnetic field. And this complex of particles and fields support a wide variety of phenomena, wave phenomena. And here are some kind of plasma waves, such as electrostatic wave. First is electrostatic wave, which is arises when electrons are perturbed from its equilibrium state, and ions considered as it making the uniform stationary neutral background. When electrons are disturbed from its equilibrium position and due to inertia, they try to come back to its equilibrium position or to mean position, and they overshoot due to inertia and start vibrating about its mean position. And this gives rise to the oscillations. And but ions are so massive here. As we know, ions mass is so greater than electrons. That's why the oscillation produced by ion is very, very small, almost negligible as compared to the electrons oscillations. So if I talk about electroacoustic waves, it is also kind of plasma waves, which is generated when plasma is composed of uh, set of two distinct groups of electrons, such as hot electrons and cold electrons. So the combination of these uh, give a rise to electroacoustic wave. I'm not going in the depth because this is not my topic. My topic is to deal with electrostatic wave, but still I want to give a few information about this. There are also inocaustic wave, which are longitudinal oscillations of the ions and electrons in the plasma, like acoustic waves traveling in neutral gas. And also there are dust ion acoustic waves. I don't have much knowledge about these, but I will tell in a brief about electrostatic waves. I have, as I was studied some of the papers of Dr. Swarniv and in plasma physics, that most of the researchers have done work by considering classical plasma, where the density of matter is low and temperature is high. Also, like, we can also find work related to the quantum plasma, but still the work is so less. And if I what is the difference in my case? I am using some kind of different perturbation technique. I will tell you later about it. So because of that perturbation technique, the whole scenario becomes so different, and it gives rise to the shock waves. Uh, so what I am using here, I am making the use of quantum hydrodynamic model uh, in order to calculate my dispersive relation and to find the structure of evolutionary plasma waves. So what is the quantum hydrodynamic model? Uh, it is a sum up of a Windsor-Poisson model and a Schrödinger-Poisson model. Windsor-Poisson model says that it is used to study quantum kinetic behavior, while Schrödinger-Poisson model is describe the hydrodynamic behavior of plasma particles in quantum scale. So the collective of these two come as QHD model, that is quantum hydrodynamic model. So quantum hydrodynamic model is derived by taking velocity space moments of the Windsor equations as in the classical fluid model. And this model consists of a set of equations describing the transport of charge, momentum, and energy in charge system interacting through a self-consistent electrostatic potential known as Bohm potential. So what I concluded here, a quantum effect come into the picture due to the Bohm potential and quantum statistical effect through an equation of state. So this is how quantum effect come into the picture. So here is my set of governing equations or basic equations. First two equations, which is a curl Ne by curl T and curl of Ne and UE over curl of X. These the first two equations are continuity equations.
Not curl, this is spatial differentiation, del del.
Okay, all right, sir. I'm sorry for this.
कोई बात नहीं.
So these two equations are continuity equations, and the third equation is third and fourth equations are our momentum equations, and the last one is Poisson equations. So in case of here, Ne is our concentration of, or I can say density of electrons, and Ni is density of ions. UE and Ui is velocity of electrons and ions respectively. If you see in the third equation, from the right side, second term, here is a eta I. It is our viscosity term. And if in the fourth equation, from right side, our last third term representing a quantum effect, or it is a quantum diffraction term. And of course, fifth equation is our Poisson equation. And now I am using Fermi degeneracy pressure here. How this come into the picture? Because when we consider density is so high, thermal pressure become almost negligible as compared to the Fermi degeneracy pressure. So I am considering here the Fermi degeneracy pressure, and if we the first equation is Fermi degeneracy pressure, but when we approximate it, or we use some mathematical tools or use some approximation, we get the equation which is a Pj is equal to 1 by 8, 3 by pi raised to power 1 by 3 Hc, and Nj 4 by 3. Here Nj is a concentration of electrons and ions, and H is our Planck's constant, and C is speed of light. And what we this is pressure term which comes when we deal under the condition of ultra relativistic plasma. So moving ahead towards a normalized scheme. Why we need normalized scheme? Because if we see our governing equations, their dimensions are different, and in order it will be very difficult for us to solve math and because in the left hand side and right hand side our dimensions should be same. So in order to do that, we make the whole equations dimensionless. For that we use normalized scheme. Here I have given a normalized scheme. Here omega c is the frequency of plasma waves, and VFH is the velocity, Fermi velocity of the particles, electrons, or ions. Here, I think everyone has explained about this in very brief, so I will not go in deep. But still, the basic terms, that is a potential. Phi is potential here, and TFH is Fermi temperature, and KB is Boltzmann constant here. After normalizing, after using normalized scheme, we get equations something like this. First and second equations almost remain same, seems like same, but these are dimensionless. And if third equations, there is an introduction of Zi in the first term of from the right hand side, and here F in the momentum equation, in the fourth equation, which is momentum equation, there is the PE, which is the pressure of electrons, Fermi pressure, and F is a constant quantity here. Here H is a diffraction term, capital H is a diffraction term, which is coming due to the quantum effect here. In the fifth equation, there is a delta. Delta is again represent the ratio of concentration of electrons and ion density. So now I would like to tell about perturbation expansion. This, if you see carefully, my perturbation expansion is somewhat different because here you can see that in the first, what is this? It is expanding e raised to exponential raised to power 0. I'm sorry, epsilon raised to power 0, and then it is epsilon raised to power 1. Then it comes epsilon raised to power 3. There is no epsilon raised to power square. So now what is this basically represent? This is saying that small perturbation brings small perturbation in the system brings very large changes or very huge changes in the dynamics of the system. This is because of this perturbation, our end result, our KdV equation is no more remain KdV. It get converted to evolutionary equation of plasma waves. And when we plot that equation, we get shock waves. Let's move ahead. Here I would like, here are my dispersive characteristic. In the first step, you can see that how the field variables vary. There is exponential iota kx minus omega t. And by considering normalization equations and using perturbation technique, I get dispersion relations something like this. And of course, there are two modes. One is fast mode and one is slow mode. And for in case of fast mode, there is a, what is the difference? The frequency of plasma wave is quite high as compared to the frequency in case of slow mode. So I am dealing with here, I'm dealing here with the fast mode. So I have plotted for fast mode. I will explain in the result section that how plot corresponding to this come as. Now, to know about the structure of electrostatic wave, here I am using stretching variable, which are something like this. Xi is equal to epsilon x minus v naught and t, and tau is equal to x epsilon epsilon raised to power 3 and t. Here v naught is frequency it is a constant. It is a constant. I'm sorry for this. When I apply, I use normalized equations and put these stretching variables and use that perturbation technique, which I have shown you. I get my result something like this. Here you can see that there I got first term, and my second term, or A is coefficient of corresponding to the dispersive term. But viscosity is not coming in the equation. So when I calculated that, or I use that perturbation technique, my viscosity term vanishes away. And also I am not getting my nonlinear term here. Here A is given in the picture. what is it? Now, after applying the boundary conditions, after applying the boundary condition, my potential is coming like this: phi is equal to phi m e raised to power minus m eta over raised to over a. So, but here is not our viscosity term. It is a in the, if you see the first equation, there is a eta is equals to I is equals to m tau. So now let's come to the result corresponding to the linear dispersion characteristics. So here you can see in the picture, I hope the picture is clear to you, but it is seems like a little bit blurred. Uh, but you can see that result is coming, the linear wave frequency is varying linearly corresponding to the wave number. But here I have used in different steaming motion values corresponding to the steaming motions, and as the steaming motion increases, the frequency corresponding to the wave number increases as well. Here I wanted to show that, but I have not inserted picture over here. When H means our diffraction term increases to very high value, like 1,000 or 2,000 or more than this, then corresponding frequency is not zero, has non-zero value for k is equal to 0. Now let's come to the result corresponding to our differential equation, which we got corresponding to our evolutionary equation of plasma waves. Picture is something like this. This is the scenario below the zero. Below the zero potential is very, very, very low. Here you, if you see, analyze, you can see that potential is varying between 0 to 1 for a different value of H. And as the value of H increases, potential become low, below the zero. But if we see above the zero and the first coordinate, as the potential increases, as the diffraction term increases, the potential become very high, very highly, and these results are representing shock waves. I would explain in the conclusion that why this is so. Under the certain critical condition, resonance activities happen due to which non-linear term vanishes away, which is basically responsible for solitons. As a result, shocks appear in the picture. This can be clarified from the perturbation expansion, which is taken into the consideration. This perturbation technique is somewhat different from the standard one. As per this perturbation, small disturbance causes huge changes in the dynamics of the system. Consequently, the concept of small approximation does not work here, and potential goes so high. Actually, I have not plotted for high potential. Here you can see that potential is vary between from 10 to 50. But if you increase the height of y-axis, the potential, you can see the very, very large value of potential here. And so potential goes so high that instead of soliton, shocks appear in the picture. It can also be said that differential equation is no more KdV. Now it is evolutionary equation of plasma waves in dispersive medium. And solution of this equation represent shocks. And the potential obtained is free from influence of streaming motion, because when we insert the value of streaming motion, or I can say value of V naught here, then our streaming term will also get cancelled, and our solution no more remain depend upon our solution will potential will no more remain depend upon streaming motion. So this was all about my work. I hope you get a little bit idea, because I made so much confusion. it was my first time. So if there is any doubt, you can ask. I will try to answer. Hello, sir, are you there?
Hello, thank you, Parveen.
Yeah.
So we have some queries. Jit Sarkar asked, the dispersion relation always increases. How can you say that it is from a shock structure? Well, it's a good question.
Can you repeat that question,
Yes,
please?
the dispersion is always increasing. So how can you say that it is from a shock structure?
Okay. Are you talking about dispersion relation?
Yes,
Dispersion.
yes, dispersion relation.
Okay, it is increasing because I analyzed that when with the increase, it is diffraction. Sorry, our diffraction term. So linear dispersion means the wave frequency tend to increase with corresponding to the wave number.
No, he is
As
asking
per
that it is from a shock structure. So it is, I think it's not from a shock structure. Rather, I would say it's every wave has got a dispersive property. It's natural to a wave. So dispersion is not from a shock, but due to the inherent nature of the wave. So I think the question, if G Sarkar could clarify the question. Okay, let me check if G Sarkar is updated. Structure of shock waves. Well, basically, I understand that there was a this since the potential is increasing, and basically it's not only a shock, it's a linear instability kind of thing. So it's, I think you go to the expression of the potential. Slides back. The expression. These are all the potentials. Yes. Here you see it is having an exponentially decaying term. So it is damped. Now, depending upon the value of M and A, if it is a positive kind of thing, then it will grow gradually. So it's an unstable mode. So I think it's clear that it's not a regular structure. That's
yes, sir.
with that stationary structure, like a KDB or a shock. So it is a kind of gradually increasing, or here it appears as a decreasing potential exponentially. But depending upon the A, what is the expression of A? Please go back.
So A is this.
A. Well, there can be possibility that A can be negative. Well,
Yes,
you see
sir.
that, yes, the total term for the students and the audience, I would say that A, I think the total term can be positive as well as negative depending upon the streaming and the Mach numbers, H and F and all these things. So P1, P2 are the constants. And if A is negative, then it will be an unstable mode. Or else it is, if it is positive, then depending upon that expression for phi, it will be an exponentially decaying mode. Yes, correct with this one. Thank you, Parveen. So it's today's session is almost to an end. I would just like to remind you of tomorrow's program. Tomorrow we have the invited talk by Professor Dimitri Batani, and as I said, it's on advanced in initial confinement fusion from 7 p.m. onwards. And before that, please go through your subject on initial confinement fusion, so that you feel better to understand. And we have student participants, a number of student participants with their oral presentations, unlike today where Praveen is the only one. And tomorrow we have Moinak Chatterjee from Barashat Government College. The title of his talk is Ion Acoustic Shock Fronts and Solitary Structures, Effect of Exchange Correlation of Electrons. And Shomo Shorkar, National Institute of Technology, Karnataka. He will be presenting on the effects of quantum diffraction on the propagation of electron acoustic solitary structure in Fermi plasma. We have Shayan Ghosh from Acharya Prafulla Chandra College, effects of exchange correlation on electron acoustic solitary structure in ultra relativity degenerate plasma. So this is tomorrow's program. And as for Parveen, I would just like to say that you just mistyped one name. So that is the relativistic degeneracy pressure which you were using and not the Fermi degeneracy pressure. Okay. So that was a correction you should include. And,
all right, sir, I will make that.
Yes. I think you have studied so many things and just mistakenly used the wrong name. That's possible because you people are quite young and new with plasma. So thanks to all of you. And
Yeah.
good evening.
Sir. Thank
You guys say good night for everyone. And basically, we have participants from Egypt who are wishing good evening right now. Well, thank you, Nora and Bakri. So we will be having Nora's talk on day after tomorrow on 9. Nora is from the Damietta University in Egypt. So we have a packed program on 9th as well. We have 2 guest speakers like today and 5 student presentations. So as of now, thank you. Thank you for your patience and interest. So tomorrow, same place, same time. Good night. Jai Hind.